All right, let's jump right in. We're going to move past the basics today and get into some seriously high efficiency and specialized propulsion systems. We're talking about the advanced engines that are really pushing the limits of speed, range, and raw power.
So just try to picture this, a machine that actually breathes the air it's flying through at 5 times the speed of sound to push itself forward. Or think about engines that get so cold they turn gas into liquid just to claw their way to the stars. That's exactly where we're going today. So here's the game plan for this explainer. We'll kick things off with propulsion right here on Earth. That's ground, sea, and air. Then we'll look up into space before we dive deep into the crazy world of ramjets and scramjets. And we'll wrap it all up with some really unique systems and a full summary.
Okay, first things first, let's start with the absolute fundamentals. How do we actually generate motion in the 3 main places we operate? We're going to start with the one we all know best, the air.
You know, when you're flying, it all boils down to a simple tug-of-war between thrust and drag. It's pretty straightforward, really. If you want to go faster, your engine's thrust has to win against the air's resistance, that's drag. And if you just want to cruise at a steady speed, you need them to be perfectly balanced in a perfect tie.
Now this is where it gets really cool, because there are basically 2 different recipes for creating that thrust. On one hand, you've got the fuel-efficient way. Think of a giant cargo plane with those huge fans. It moves a massive amount of air, but it does it pretty gently. Then you have the other approach, pure power, like a fighter jet. It grabs a much smaller amount of air and just blasts it out the back with incredible force. So it's always a trade-off, right? Endurance versus pure, raw power.
And on the ground, sure, we're all used to wheels and axles, but the future is looking a lot like maglev. This tech uses powerful magnets for literally everything, lifting the vehicle, pushing it forward, and steering it. And because you've gotten rid of friction completely, you get a ride that's smoother, quieter, and way faster than any traditional train could ever hope to be.
Down in the water, it's pretty much all about propellers, but what's turning them is what's interesting. A lot of ships use diesel or even liquefied natural gas, which is better for emissions. But for those really long missions where you can't just pull over to refuel, the armed forces often turn to the unbelievable power of nuclear reactors. They just generate steam to power massive warships and icebreakers for years at a time.
All right, so we've covered Earth. Now let's turn our attention upwards and talk about the totally different set of challenges that come with pushing vehicles out of our atmosphere and into the vacuum of space.
So just getting to space takes the brute force of a chemical rocket to break free from Earth's gravity. But once you're up there, the whole game changes. For those long trips across the solar system, we switch over to super efficient things like ion thrusters. Now they produce a tiny amount of thrust, like really tiny, but they can keep it up for months, even years. And over time, that gentle push builds up to incredible speeds for deep space missions.
And now for the main event. Let's talk about the engines that live on the absolute edge of speed and altitude. We're talking about hypersonic travel, and it's powered by engines that are almost beautifully simple in their design, but just mind-bendingly complex in how they actually work.
Say hello to the ramjet and the scramjet. I mean, just look at them. They're basically hollow tubes, like stovepipes. The absolute genius here is that they have 0 moving parts. No turbines, no compressors, nothing. Instead, they use the vehicle's incredible forward speed to literally ram air into the engine, compressing it just enough for combustion.
And this table just lays out the key differences perfectly, but the most important thing to see here is that very first line, airflow at combustion. A ramjet actually has to slow the incoming air down to subsonic speed before it can ignite the fuel. A scramjet, though, does what seems impossible. It keeps the airflow supersonic through the entire engine, even during combustion. And that is the secret sauce that lets it fly at insane hypersonic speeds of Mach 5 and way higher.
And this analogy just nails it. Think about it this way. A ramjet is an amazing runner, no doubt, but it has to slow down just a tiny bit to take a good breath. The scramjet, though, that's the super athlete. It has figured out how to breathe perfectly while going all out at a full sprint. It never, ever breaks its stride. So why bother with all this incredible technology? Well, the payoff is huge. First, since they breathe air, they don't have to carry their own heavy oxygen tanks like rockets do. Big weight savings. And their simple, no moving parts design makes them tough. But, and this is a big but, there's one major catch. They can't start from a standstill. They need a rocket booster to give them a massive push just to get them up to the speed where the whole ramming air thing can even start to work. Okay, let's get into our last section on specialized systems. We're going to look at another type of high-performance engine that's built for the vacuum of space, the cryogenic rocket. And then check out a very unique dual-role military system.
When we say cryogenic, we're talking about serious cold. I mean, unbelievably cold. We're supercooling gases like oxygen and hydrogen down to below -243 degrees Fahrenheit. That turns them into dense liquids, which lets us pack a ton of propellant into a much smaller tank.
And why go through all that trouble? Well, the reward is a massive jump in efficiency. And this number right here is the whole story. A cryogenic engine needs a whopping 30% less fuel to get the same exact result as a regular rocket. I mean, think about that. For every 100 tons of fuel a normal rocket needs, a cryogenic one only needs 70. That incredible efficiency is why they're essential for that final push to get heavy satellites into really high orbits.
And finally, let's look at a pretty specialized piece of military hardware, the ADATS. This thing is a mobile system designed to do two jobs: shoot down aircraft and blow up tanks. Now, since those are two very different targets, the operator has to make a critical decision. They have to select the right warhead for the job before they launch the missile, tailoring the weapon perfectly to the threat.
Okay, we have covered a ton of ground. So, let's take a second to pull everything together with a quick review to help make sure all these key ideas really stick. This table is a fantastic final comparison. It really boils everything down to the most basic difference. Where do these engines get their oxygen? An air breather, like a scramjet, scoops it up from the atmosphere, making it perfect for flying really fast inside the atmosphere. But chemical and cryogenic rockets have to bring their own oxygen with them, which is absolutely essential for launching into space and flying around in a vacuum.
And hey, for anybody out there studying this for a test, this one's for you. Here's a super easy way to draw the difference. Just draw two rectangles. For the ramjet, you put a little diamond cone at the front to show how it slows down the air. For the scramjet, just draw a straight arrow all the way through. It's a quick and easy visual that gets the main idea across perfectly.
So, let's do a super fast recap. We learned that air propulsion is that constant balancing act between thrust and drag. On the ground, maglev uses magnets to get rid of friction. Way out in deep space, those super efficient ion thrusters rule. The big difference between a ramjet and scramjet? Subsonic versus supersonic combustion. And finally, cryogenic engines give us that huge fuel efficiency we need, while the ADAT system is a specialized 2-for-1 weapon.
And that brings us to one final thought to leave you with. Why does a scramjet have to be launched by a rocket? Why can't it just start up on its own from a dead stop? I mean, think about its design. The whole thing only works because of its own incredible forward motion. It's a fascinating paradox, isn't it? An engine built for ultimate speed that's completely useless when it's standing still.